One night to be confused, one night to speed up truth. We had a promise paid for.
And welcome to the video on limits and continuity. Okay, so first of all, we're going to start with continuity at a point. That's always the best way to start, is from a point perspective, one by one. So continuity at a point. So what this means is that we're going to, first of all, have assumptions. So we're assuming that f of x, some function, so that f of x is defined on an open interval, so that means not including endpoints, interval, containing, so this interval contains some x value which is equal to c, some constant, okay? So then f of x is called continuous at x equals c if, so this is a big if the following is true. The limit as x approaches c of f of x is equal to f of c. Okay, so what we're going to do is actually, this is very important, pretty crucial here. So what we're going to do is break it down. So I'm going to look at the left side first. What does this even mean? So first of all, this limit has to exist, okay? So for this limit to exist, that means that x, as it approaches c from the right side of f of x, that has to equal the limit as x approaches c, our value c, from the left side. And these positive and negative signs mean a little bit more than c and a little bit less than c, okay? So for example, what we want for this limit to exist is this second box here, okay? So if we were to have a function, for example, let's say f of x looks like this, and then here's point c, okay? So here's c, our x value of c, here's our x and y axes, and this is our f of x graph, or our curve, okay? So from the left side, we'll go from the right side first, so c plus on the right side is over here, so we're coming from the right, so it's approaching a certain value here, okay? And then from the left side would be on this side, so then we're coming from this side, and it's actually approaching the same value. So in this case, the limit, this left side exists, this limit over here. So that's good. That's the first part. You have to have a limit that actually exists. An example of when it wouldn't exist is called, it looks like this. So let's say we have the same graph here, same point, but then it has this little jump, okay? So something like that. So this is still our f of x graph. It's defined at every point, okay? This happens to be point C, let's say. But this time from the right side, we're coming from the right side over here. So the limit from the right side is all the way up here. But coming from the left side, here we go. So it's actually going to this point down here. And these two lines that I just drew, the horizontal ones, they are not equal, or they're not at the same place. So the limits, the one-sided limits do not agree, okay? The limits from each side do not agree, so that means that this thing over here, the left side, the limit as x approaches c of f of x, doesn't even exist. So this is definitely going to be discontinuous. So discontinuous, all right? Okay, and this one actually, just in more detail, this one here that I just drew, because the graph here, so I'll make it bold. So here's the graph coming from the left, here's our point, and then it continues on going in this direction, okay? This is called a jump discontinuity. So I'll just write it down here, a jump, it's referred to as a discontinuity here, because you jump from like one level to another, okay? Alright, so this makes it obviously discontinuous. This function is not continuous at x equals c because we have a jump here, so the limit doesn't even exist. So the left side is not even fulfilled of this equation here. I'll call it equation 1, okay? This is the number one most important equation about continuity. Okay, so let's look at what if we were to have the limit existing, like the one that I'm boxing here. So what if the limit exists? I'll continue this on the next slide. So I'm going to write our number one equation up here again. So limit of, as x goes to c, or approaches c, of f of x has to equal f at point c. at our x value of c. Okay, so let's say that we know that the limit exists. So let's say we have some graph that looks either like, let's see, so I'll just draw that same one, right? So here's point C, x value of C, here's our x, and this is our f of x, and this is our y. Alright, so the limit obviously exists, okay, so that's good, and f of C, so the function evaluated at point C equals that limit. So the limit is at this line here, at this level, at this y value, and the f of c is at that same level. So this is good. This means that both things are fulfilled. So the limit exists, first of all, and the function at that point, c, agrees with the limit. Okay? So kind of like three components. The left side limit agrees with the right side limit, agrees with the value of the function at that point. So this is good. This is continuous. Okay? So this is continuous. Continuous. Alright, let's look at an example where there is a limit. The limit exists, but the function is still not continuous. So let's say we have something like that, right? So we're going along. Here's point C, and we're still going along, but here's the point up there. Okay, so this is our x value of C. This is x, this is y, f of x. Okay, so here, let's look at the limit part first of all. So coming from the left side, we're approaching this value here. So we're approaching something at that value. And then coming from the right side, we're approaching that same value, right? So the limit exists, definitely. So here we have limit exists. Limit exists. Okay. But at that point, our f of c is actually all the way up here. It kind of did this random thing, and it decided to, the point itself decided to jump. Not the entire graph, like there aren't two different levels going on as far as the left and right side, but the point itself decided to jump out of the way, or remove itself from the rest of the graph. So this one here, what we see, is called, this hole here, that's called a removable discontinuity. So removable discontinuity. I'll just abbreviate, discontinuity. Okay? So something like that. Alright, so again, limit exists, but the point jumped, so it is a removable discontinuity. Okay, so now we'll go more in detail and look at different cases of when you can get discontinuities and when you can get actually something called one-sided continuity. Okay, so here we've kind of already seen an example before, but I just didn't point it out at the time. So this is for jump discontinuities. I can't write. Okay, discontinuities. All right, so there we go. So an example of this would be a left continuity. Okay, so this is at x equals c if we have the following: if limit as x approaches c from the left, that minus sign means from the left, of f of x is equal to f of c. So a picture of this would look like the following. So we would have something like, here's our f of x, and we're going along, we have our point, but then it jumps, and the right side continues. So this one means, so here's our point C, right? So from the left, we're going along. So this is our limit from the left. It's at this level here. And then from the right, though, we're all the way up here for our value. But the point f of c exists on the limit from the left, right? So because we have that agreement between the left side limit and the function itself at c, then this is called a left continuity. So a right continuity, on the other hand, so right continuity would look like the opposite, at x equals c, if, and we're going to have the same exact thing, except for now we're going to have x going to c plus, so a little bit from the right of c, f of x is equal to f of c. So this one, on the other hand, would look like, I'll just draw the same thing, but this time the point f of c moved to the top. So now, see how from the right side we have our limit up here, from the left side we have our limit going to somewhere down there, and the point itself at c agrees with the right hand side of the limit. Okay? So anyways, and both of these are jumps. because the right and left hand continuities do not exist, or sorry, continuities. The limits, the right and left hand limits do not agree with each other. Okay, and we can even have, along with this, we can have no-sided continuity, where we would have just a jump. So let's say we have the left side here, and the right side over here, and our point is in the middle, or even like down here or up there, either one. But anyways, so at this point C, we have our left hand limit, okay, that's down there. Our right hand limit, okay, that's up there, and our f of C is at a completely different value. So here we have absolutely no-sided continuity. That's not actually a term, I kind of just made it up, but this is just a difference showing contrast between right and left continuity, right or left continuity. So this one basically has neither of those. So neither right nor left continuity, because the value of the function at C doesn't agree with neither the right nor left hand limits. Okay. All right. So now for another kind of discontinuity, this is going to be our last one. So this is called an infinite discontinuity. Discontinuity. Okay. So for this one, what we have, if one or both sided limits is infinity. Basically, infinity or negative infinity or anything of the sort. Okay, I'll just put infinite. Infinite. There we go. Okay, so is infinite in some way. So examples of these would just look like, so if we were to have, like, here's our point C, okay, and we have the graph going along, and then it goes up and up and up and up and up and up and up. That wasn't supposed to bend in at the last moment. But then, and on the other side, we have something like that. Okay, so at C, you're going to see that we have a vertical asymptote, right? Because the graphs do not touch that line, or even if they did a little bit, but if they keep going up, then this means that, so as x approaches C from the left, our limit is going to equal positive infinity. It's just going to keep going up and up and up. And from the right side, we're also going to have a positive infinity. Okay, or we could have, here's another case, just so you know that we're open to different kinds of cases. So here's C, all right, here's our point C, and what if we had the same thing from the left, okay, but on the right side we had some graph coming down forever, okay, and we have a vertical asymptote at C. This time from the left side we're going to have our limit still be infinity, positive infinity, because it's going to go up and up and up. But from the right side, as we get closer, as the x value gets closer to C, our graph continues downward. It continues going down and down, down and down and down to negative infinity, which is also an infinite value, right? Negative infinity. It's just like positive infinity, except for going the other direction. Okay, and then lastly, I just want to say that introduce this case where at C, you might have one of the sides, one of the one-sided limits, be a finite value. So here's our C, and what if we have something like that? Okay, so it actually exists there, but one of the sides is still infinite. Okay, so what do we do with this? So from the left side, it's actually a value, right? So this limit exists, the left-sided limit exists, and it actually is a non-infinite point. It's a definite point. Okay, so we have some kind of f of C here, but from the right-hand side, as x approaches C, we're going up and up and up, and this is positive infinity. Even though f of C is defined and not infinite, even though this exists, then we still have this x approaches C from the right side. Since that is still infinity, then we still consider this an infinite discontinuity. So this is still an infinite. Well, all of these, I was just talking about the last one, so all of these are infinite discontinuities. Okay, so now we'll move on to the basic laws of continuity.
One night